Hey everyone. Last time in class we sort of introduced position vectors. So we're now sort of entering the topic of motion in 2 dimensions. In 2 dimensions, I mean things in the XY plane. So this sort of mimics how things will move in the real world a little bit more accurately. Let's look at the first example I have. We have this graph here. We have the XY axis. So X and Y. So think of this blue line that I have, drawn here. Think of that as like a ball flying through the air. This is a path of a baseball at different moments. We'll say at one moment, the ball is right here. We need to find a way to be able to sort of locate that. So on this axis, or on this sort of graph I have here, I'm going to be able to draw this position vector, be able to find out where exactly this ball is. I'll be able to call that R, and we'll just say R1 in this case. And normally, this position vector R, let's say in general, it's a made up of a little bit of a horizontal component and a little bit of a vertical component. So that is this that I'm going to be writing. Yj hat. So if you could see this line, it's a little bit moving over to the right and a little bit moving up. That sort of forms this vector. Okay, cool. So we can find out where this ball is at this moment. But the problem arises, we don't live in sort of a stagnant world. At maybe like 1 second later, the ball is going to travel along this path, and let's say the ball now reaches over here. We would then have to find a whole new position vector to locate the object. I'll call that R2, vector R2. You see, we have to find out, okay, that's a new X component. Let me go like this. New X component as it goes this way, this much, and a new vertical component, it travels up. And that's where we find the ball at that moment. So these position vectors, if we want to find the difference between the two, that's this line. This is the delta R. This is the change in position as the ball travels in time. All right. And we can maybe make this a bit more clear. I'm not going to fill out this graph on the right here. I have an equal graph on the next slide. So we can use this position vector here, we can use this to sort of be able to show how an object will move. Let's go to the next slide. So I have a bit of a larger picture here. It's maybe make it a little easier to show. So we can use this position vector that I called R. We use it exact same way as we did in the previous chapter with just position. So we can use that to find velocity, and then we can use the velocity to find acceleration. It's all pretty much exactly the same. So we can use that position vector to find velocity. Delta R. Well, I guess, yeah, delta R for delta T. And then, so this is the average, I should say. Average. And then instantaneous velocity. And this is sort of the formal way to write it. This is the limit of delta r over delta t as delta t approaches 0. Okay, so maybe it would have been good if I could show that other graph, but I will probably make that on this one as well. So let's say we have the same, a similar example. We have this path. The ball travels along this blue line. And at one point, the ball is right here. And at another point, the ball is up here. And this is a two-dimensional graph. This is x, and this is y. So you can think of this as just like a side view. This is just a side view of me seeing someone throw a baseball. All right, and we could see the change in position is that delta r. That's right here, delta r. And that is made of a change in the horizontal component, delta x, and the change in vertical component, delta y. So we can use this delta r. We know that it's made of, that x I hat plus y j hat. We use those two components and we just separate them. Maybe I could show that a bit more clearly with an example coming up. We see that we can look at this point right here. Let's say, maybe I can make it a bit clearer. So this point right here, let me make it red. This point right here, I'm going to call point 1, has the coordinates, I'll say x1 and y1. And I'll make the other point blue. This point up here has the coordinates x2 and y2. Now you can see that there will be a different x value for the first point and the second point, and there's a different y value for the first point and the second point. And so we would just come in here and write out that this change in distance, delta x, is x2 minus x1, as well as this change in height, y2 minus y1. Hopefully that's what this will maybe be a bit more clear when I have this phrase pop up. The components will be separate. So the components of these 2 points sort of tell you where the thing is, but I'm just going to separate all the x terms to one side. I'm going to separate all of the y terms to the other side of this sort of triangle I'm making. How do we actually use the, or how do we actually find out where something is? It seems like now we're using the position vector, and maybe the velocity can be the same, but how do we actually use them? Well, it's going to be exactly the same as we have before. We're going to have a horizontal version, and we're going to have a vertical version. So let me write these out. The horizontal version is typically labeled x. So these are going to be the exact same kinematic equations as we have already learned before. So I'm only going to do the 4, but I'll try to write these out fairly quickly. So there's v, and this is where we need to be more specific in how we are labeling these. So this is v sub x. So that's just like a little name tag on this velocity term. V equals v not x. So this is the initial velocity in the horizontal direction. Plus acceleration in the x direction, so the horizontal acceleration, times the change in time. And then we have the next equation, which looks something like this: x equals x naught plus v naught x now t plus 1/2 the horizontal acceleration times t squared. The third one will look like this now. Vx, so this is the velocity in the horizontal, or you could think of, let me see, you could think of this and this as the final velocity. Equals v naught squared, this is the initial velocity squared, plus 2ax times delta x. This is the change in position in the horizontal direction. And that last one, I'm going to write it as, I'll write it as this. Equals 1/2 vx squared plus v naught x squared times delta t. Okay, so these are the exact same things that we've seen before, except I've added a little bit more labeling on these. So all of these terms have a relation to how the thing moves horizontally. So this is the, there you go. So this is the horizontal final velocity. This is the initial horizontal velocity, the horizontal acceleration, and time doesn't really care about direction, so that's why there's no labeling on the time. So we have next the vertical components. These are the exact same things, except they're going to be used for motion that is purely vertical. V sub y. So now we're labeling this one as the final vertical velocity. Equals the initial vertical velocity plus the vertical acceleration, delta t. We have the vertical change in position, y naught, plus v naught y t. And then everywhere there's an x over here, I'm just going to write it as a y. That's just to remind me that I'm only looking at the motion of, whatever's in the problem. I'm only looking at the motion that is vertical when I'm using these equations. delta y. Oh, I made a mistake over here. So over on the bottom left, right here, I had a delta y that should not have been, should have been an x. Okay, over here, down on the bottom right, that is delta y. Then we have 1/2 v y squared v naught y squared delta t. Okay, so whenever we want to figure out how far something moves horizontally, we use horizontal kinematics. Whenever we want to figure out how far something moves vertically, or how it interacts with anything vertically, we'll use the vertical kinematic equations. I have a few examples that I can show that'll maybe make this a bit clearer. When we get into projectile motion, we'll see that as things are sort of moving through the air, as I throw a football or throw a baseball, or even if I just roll something off of a table, it will exhibit some projectile motion. Projectile motion is just a combination of the two coordinate systems, or of the two components, I should say. So let's look at the case where we have a, let's see, we have a cannon. And there's no gunpowder, there's nothing firing out the cannonball. And I just sort of let the cannonball go right from the end of the barrel. There is only the vertical component acting on the ball. It has no horizontal components, so it's not going to fire outwards, it's only going to travel straight down. And how is it going to travel straight down? Well, from the previous chapter, we've seen that things that are moving vertically near Earth, they accelerate downward. So this is experiencing an acceleration downward. And typically this is just related to gravity. Gravity is negative 9.8 meters per second squared. And that's sort of represented in this picture. It's sort of, imagine you're taking a steady picture every second, and the ball will get faster and faster as it starts to accelerate downward. Okay, well, what if we have the case where, let's say we're out somewhere where there is no gravity. Let's consider the horizontal case. This would be the case if there was no gravity. So seeing that picture on the left, so try to ignore this when we're looking at this side. So this is the case when there's no gravity. As the cannon is fired out, and if there's no gravity, the ball is going to move at a steady rate. So nothing is affecting the ball anymore. You imagine you're out in space, free floating somewhere, and we fire this cannon. The ball will come out and there's no friction. There's nothing happening. So if we take a picture every second, we can see that the ball is moving at this steady rate. It's there's a constant velocity in each of these pictures. That's why they're evenly spaced out. And it's this sort of combination of the two. So down on the real world, down near Earth or anywhere with gravity, you know, there's a little bit of this happening. Well, I should say that not just a little bit, this entire case is happening, but it's just combined with this. So how can we combine those two? Well, look, something like this. So we can see this is describing the arc of a projectile as it sort of comes out. It's moving very quickly to the right. But then it is sort of pulled downward. It's accelerated downward by gravity. We can see from these dotted lines that are matching up. Let me see. So see, the dotted lines still show that the ball is still moving to the right at the same rate, except now over time it is beginning to fall downward with that little bit of acceleration. The value is getting larger and larger over time. And that's combination of the two creates this sort of parabola here. All right. So how do we know where and when we should use those equations? I can maybe visualize this example. It's, you know, a little bit of that horizontal component, and you mix it with the vertical, and you get this path of the projectile. But how do I know when and where to use them? Does this work for you know, some other type of projectile? Let's go to another type of projectile. We'll see something like this. This could be like a football pass of some kind. So if I'm going to pass a football to someone else that's really far away, I don't want to throw it completely straight or completely horizontal to the ground, because I know that the ball is going to just fall down and hit the ground before it reaches them. So I have to sort of aim the football upwards. So me aiming the football, so I'm over here, I'll have to aim the football upwards. And I have to give it a certain amount of initial velocity when I throw it. So in that initial velocity, that's sort of this black arrow here, that's sort of, let me make it a different color, I'll do yellow. So that initial velocity, actually that's a bit too bright, I'll do orange. That initial velocity is at an angle. And that angle that I throw this ball or any sort of projectile, it has a little bit of horizontal components and it has a little bit of vertical components. And this sort of picture is showing you how the two change over time. So let me get rid of this. So I throw it at a certain velocity at an angle, at a specific angle, and we can look at the horizontal component. Let's look at this horizontal value, the red arrow pointing to the right. It maintains that horizontal, so there's right there, as well as right there. I could keep going. It maintains that constant horizontal velocity all the way through the entire path. So there's that. But what happens to the vertical component? So I throw it at an angle. I throw it at that, you know, steep angle, and it has that large vertical component at the beginning. Let's see, let's do this. So it's a large vertical component in the beginning, but this is just like throwing a ball in the air. Gravity is going to accelerate it downward. So that's going to make it slow down as it reaches the peak up here. And right at this peak, up here at the top, its vertical velocity is 0. So imagine I throw a ball, instead of on this sort of parabola like this, if I throw a ball straight up in the air, a ball is going to get to a point where it will slow down and stop, and its vertical velocity is 0, and then it will start to accelerate back down. So I'm sort of seeing the two mapped onto one another. I'm going to do a little example of something like this right now. So you throw a baseball in the air with an initial velocity of 10 meters per second at an angle of 60 degrees above horizontal. This is almost ideally, this is almost exactly the same as that previous slide. What is the maximum height that the baseball reaches after you throw it? Okay, so we have, let me do a little picture. I throw the baseball at an angle of 60 degrees above horizontal with an initial velocity of 10 meters per second. Okay, so how do we find this maximum height of the baseball? Well, we need to split the components into their like values, or their like terms. So we need to think of this problem as, and let me draw the picture a bit more fully. So we have that, something like that. We want to find out what is the maximum height right here down to here. Right? So this is kind of like one of those previous problems where I threw a ball straight up into the air. And that was just the ball going straight, directly upwards. It wasn't going in this parabola. But what was the sort of direction, or the velocity that we needed? We needed to know how fast is it moving directly upwards. So we have this velocity, the initial velocity, and it's sort of off at this weird angle here. We need to know, let me do a different color, that velocity is made of a horizontal component, and it is made of a vertical component. There is a horizontal velocity and a vertical velocity. So these two together make this hypotenuse here. So then we can use equations that we've previously covered on a ball just moving straight directly up into the air. And one of the equations that was helpful was this one right here. V y say delta t. That's delta t. All right. So this is the equation that can help us out with this problem. But now we see why we need to split this initial velocity that we're given we're given this value. Now we see why we need to split it up into its components. We have the initial, we have to find this initial vertical velocity right here. So how can we find that? So if this hypotenuse is 10 and the angle is 60, we are going to use the trigonometry review from earlier. So we want this value. We want the value of the blue side of this triangle. So that's going to be the opposite side, and we already know the hypotenuse and the angle. So we're going to use sine. Sine of the angle is opposite over hypotenuse. And so that means that sine of 60 degrees equals opposite v naught y over hypotenuse, which is 10 meters per second. And that carries over to being v naught y is 10 meters per second times sine of 60. And I don't have that pre-done. Let me do that right now. So 60 sine times 10, we have 8.66 meters per second. All right, awesome. So now we have that value. That is the value of how fast the ball is moving upward. So we launch it at an angle with a value of 10. We say we wanted to only figure out how fast it's moving up. So it's going 8.66 meters per second upwards. Okay. So let's look back at this equation up here. What else do we need to know? So we've figured this out. What else do we need to know? What is the acceleration in the y component, or the vertical acceleration in this problem? Typically on Earth and near things with a large amount of mass, this will be the gravity. The value of the acceleration of gravity goes right here. And what else can we maybe assume? You know, we're only given this value, 10, and this value, 60 degrees. Well, we know that we're going to throw a ball into the air. So we're going to throw this ball into the air, and then at this highest point right here, this highest point, it's not going to be moving. So I'm going to throw it up into the air, and at this highest point, it's not going to be moving upwards anymore. It's going to stop. So its vertical velocity, so its vertical final velocity, right at the peak right here, will be 0. So this final velocity is 0 at the peak of this sort of parabola. And we could put in gravity as well. And it looks like, so let me make sure, I'm going to make that negative 9.8 meters per second squared. And this will actually tell us, it's not going to give us the value of, you know, this distance yet. what we are going to find out the amount of time. So we don't know how long this ball is in the air. So how much time does it take for the ball to go up to the peak? And once we find the time, that will be, a valuable little clue for us to use later on. Alright, so let's solve for time right here. So let's put everything else on one side and have time on the other of the equal sign. So let's say delta t equals, subtract that over, and then we got to divide 8.66 that equals 0.88 seconds. So this is the amount of time it takes for the ball to go from the starting position up to the maximum height up here. Okay, we are almost there. So we have the final and initial time velocity. We have acceleration. We have time. We only we now have everything we need to solve for the displacement of its height. So we can use this kinematic equation. We can say y equals y naught. So I'm going to write the full thing out. I'm going to write it how it's normally written, and then I will change it in this next line. So let's see. So I'm going to say that where I launch this ball, where I throw the ball from, that is going to be 0. So this initial y naught, initial height, that's just 0. Okay, we have to remember to put in gravity for this acceleration here, and the rest we should know. So let's rewrite this equation, but with the things we know. So I'm not going to put the values in yet. I'm going to write it like this. Y equals v naught y, the initial vertical velocity, is t, minus 1/2 g t squared. Alright, now I'm going to take this equation that I know everything except for y, and I'm going to plug in the values. So y equals, this is the initial 8.66. I should include the units, but I'm running out of space. Actually, no. I can just make more space right here. So I'm going to rewrite it right there instead. So y equals 8.66 meters per second times the time, 0.88 seconds, minus 1/2 9.8 meters per second squared, 0.88 squared. And I'm going to do these multiplications in 2 steps, so I don't make a mistake. So I'm going to say 8.66 7.6 2 minus 9.8 0.8 3.79 7.62. So we have a height, a maximum height of 3.82 meters. So the units on that is meters, and units are seconds squared meters. Okay, so that is the answer to that first problem. This first problem right here. You see I ran out of room to do that second problem. Let's see. Oop. To solve that second problem, I changed the slide on accident. To solve that second problem, what you do is just about the same thing, except now you're going to go from the top back down to the ground, or to the original heights of 0. And really what you're going to find is that if you launch any sort of projectile and it raises up into the air and falls back down to the same heights, so I'm just going to write it over here on the side. So up in the air and back down. If it lands at the same height, that means however long it takes to go up, will be the same amount of time it takes to come back down. So that's sort of the quick way to figure that out. A lot of problems, including homework problems, don't have you sort of throwing like a projectile and landing on the same sort of height. A lot of problems might be like this. You throw a ball and you need it to land maybe on the roof of a building. And then how can you do that? Well, that's sort of the case where you go from 0 to the max, and then you go from the maximum height back down to however far that is. Alright, so I think this is enough of a hint on maybe some homework problems. But this sort of thing, let me see, this sort of example wasn't on that previous slide. So let's see. These equations were given for the exam, or the quiz that we had. Let's see. I think that's pretty much all I had for this lecture. If you guys have questions on any of this, or questions on the homework, it would be better if you email me directly or come to my office hours. I want everyone to sort of be on top of this, 'cause this is sort of the majority of what we're going to be using. We're going to be using a lot of sort of kinematics, things moving. We're going to be very familiar with these equations by the end of the semester. Alright, so that is it. I will see you guys later, and I hope you have a good weekend. Bye-bye.